All right, ladies and gentlemen, this is part 3 of Aviation Weather for Professional Pilots, or I think I'm going to name the series either Meteorology for Professional Pilots or Aviation Weather for Professional Pilots, but this is part 3. If you haven't, this is a building block process, so if you haven't looked at 1 and 2 of the series, I recommend that you go back because it's a building block process. We were talking about temperature and why temperatures vary, and it has to do with latitude and topography, or just the ground and water areas and stuff like that. All right, so temperature variations with topography are not related to the movement or shape of the Earth, and these are temperature variations induced by water and terrain. Excuse me. So again, the topography, we get temperature variations just due to land and water areas. All right, as the water absorbs and radiates energy with less temperature change than does the land. Large deep bodies of water tend to minimize temperature changes, while continents favor large changes. So continents, large areas, they favor large temperature changes when we get a lot of heat or solar radiation, and the land actually releases heat quicker when it gets cold. One fine example, wet soil areas like swamps and things of that nature, they suppress temperature changes because of the moisture in the ground. This isn't really not just regular soil where we get big temperature changes. This is warm, moist, thick vegetation. It controls temperature changes. So that's why trees are good for maintaining balance. Don't chop down all the trees, people. I'm not a tree hugger, but I'm just saying. Now, this area will resist major temperature changes, while this area, like desert areas, these places are like where you get the major temperature changes. The desert can be very, very hot, 100 plus degrees during the day, and it could be very, very chilly at night. And then another thing affecting temperature variations with altitude is lapse rate, which we're going to go into. All right, now we're just imagining the space shuttles down here getting ready to launch, and it's like 72 degrees on the outside air temperature gauge, 72 degrees. As we increase in altitude, we get a drop in temperature, and that's called a temperature lapse rate, or just lapse rate. Standard lapse rate in a perfect atmosphere, at which the atmosphere is never perfect, or we won't call it a perfect atmosphere, we'll call it a standard atmosphere. A standard atmosphere is one in which we calibrate our flight instruments and things of that nature. We take that into consideration. But in a standard atmosphere, as we climb, we should lose 2 degrees Celsius per 1,000 feet, or 3.5 degrees Fahrenheit per 1,000 foot climb. So in the next slide, now we're just simulating our outside air temperature gauge. We went from 72 on the surface, and then when we get up to altitude, it dropped. Now that is exaggerated a bit, but my thing was I wanted to stress down here at the bottom. When we were down here at the bottom, it was a nice warm day, and as the altitude increases, the temperature drops because of our temperature rate, our lapse rate. Again, just to recap, the troposphere, since we're talking about the weather changes, we're going to get a drop in temperature as we climb until we get to the tropo change, pause, stop. At the tropopause, this constant, or this lapse rate, it stops. All right. Now we still lose temperature, but not at 2 degrees Celsius per 1,000 feet, or 3.5 degrees Fahrenheit, whichever. Because, like we told you, in aviation we use 2 temperature scales, Celsius and Fahrenheit. So if you're using Fahrenheit, you should expect 3.5 degrees of temperature drop every 1,000 feet you climb, and if you're using Celsius, you should expect to lose 2 degrees per 1,000 foot of climb. So that brings us back to the tropopause, because this temperature change is where it stops. Now I have a chart that I'm going to show you, and you can pause here if you like. This is our altitude. I want you to focus on altitude. If you want, you can focus on pressure ratio and temperature. Now this chart comes from Aerodynamics for Naval Aviators, another good book you can purchase. Well, all the Navy guys, the ASTB, Aviation Selection Test Battery guys, United States Navy, United States Marine Corps, and for marine aviation applicants, and Coast Guard actually take the ASTB. So the Aerodynamics for Naval Aviators is definitely a book that I'll also recommend that you need to keep in your pilot library, and there's a wealth of information in there. But when we talk about aerodynamics, we have to talk about the atmosphere, because the plane is flying through the atmosphere. So back to my point. Focus on altitude. You can look at pressure. And we could look at temperature is what I'm really concerned about. So in the standard atmosphere, at sea level, we should have 59 degrees Fahrenheit. When we climb, we should be losing about 3.5. Because we're you're thinking about the Fahrenheit scale, we should be losing 3.5 degrees Fahrenheit per 1,000 feet. It's roughly that, because we went from 59 and it'd be 55.50 if it was exactly. So like I said, it's around near like my people in the South, nearabouts. Nearabouts not even a word, but you get my meaning. You get the gist of what I'm saying. So when we get going and we climb like our space shuttle here, at sea level we should have 59 degrees. So we get a constant drop every 1,000 feet. It starts at 0, 1,000, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20,000. This star represents what we call the geopotential of the tropopause. Just tropopause for our purposes. Just that star indicates where the tropopause is. So we get a temperature drop. We're at 59 degrees. We get to 10,000 feet. We almost lost. Yeah, we lost half. All right, so we had a 30-degree drop just by a 10,000 foot climb above sea level. And then we get to 20,000 feet. Now we're in the negative numbers. It looks like negative 12. And then we get to 30,000 feet. We're at negative 49 degrees. All right, so we get a continuous drop, our lapse rate. And then at the tropopause, where the star is, look what happens at the tropopause. We get negative 69.7, 40,000 feet stays there, still there at 50,000 feet, 60,000 feet stays there, the temperature remains constant. So at the tropopause, tropo, change, pause, the temperature change stops at the tropopause. Alright, and it's gonna, let's see here, at about, looks like at 85,000 feet, and most of us will not be flying at those altitudes. Then the temperature drop stops or the constant temperature stops, and then it gets a little bit warmer, up to 100,000 feet. Okay, I just wanted to make sure. So, I just wanted to make sure I got all my points across. Another thing, I do a lot of like simulation videos for people that need help understanding the Embraer 170. Here, this green band represents what ATIS, the Automatic Terminal Information Service, is saying. On the surface, and you can see the gate there and all that and everything, the temperature is 11 degrees. When we get to our cruising altitude of 18,000 feet, you can't see the negative symbol that well, but it dropped to negative 22. So I want you to understand that as you increase altitude, you should reduce temperature. The temperature should get lower. And we talked about this, the standard atmosphere. This will be a perfect atmosphere, but this is mostly for like instrument calibration and aerodynamics when people are designing wings and things of that nature. So it's normal to see a decrease in temperature as altitude increases. Now, sometimes the lapse rate is inverted, and in that area, in that type of situation, we call that a temperature inversion. The lapse rate is inverted. Down here at the bottom, it was cold, and as we climbed, it got warmer. Basically, what it did was just reverse it. So down here at the bottom at launch of the shuttle, if you saw 23 degrees Celsius, and then the pilots, they get up here and they're like, hey man, it got warmer, 72 degrees. That's when the pilots would say, hey, we are, this area, there's a temperature inversion in this area. All right, so the lapse rate is inverted. Lapse rates or temperature inversions are wonderful. I won't say wonderful. It's a breeding ground for thunderstorms. That's what I'm trying to say. When the temperature increases, as altitude increases, you're in the area of a temperature inversion. Temperature inversions are normally, they normally occur in areas good for thunderstorm development. All right. Now, like I said, you got in this situation, in normal condition, you have warm air on the bottom. As we climb up, we should get cold or lower temperatures. In the temperature inversion, we got a warm layer of air. So that would indicate to me that there's some type of, there could be a warm front coming in, and we'll talk about that later. I don't want to get too far ahead of myself, but just for our purposes, the temperature inversion, we got the cold air on the ground, and as we climb, it gets warmer. Now, at the upper parts of the atmosphere, it's going to get cold again, but this warm air is not characteristic of what I would call, I don't want to say normal, but I guess I could, like a normal atmosphere where, you just have a regular bright blue day, sky's blue, couple clouds in the sky, as opposed to something like this. These are cumulonimbus clouds. Cumulonimbus clouds. Cumulonimbus clouds are what we would call thunder bumpers. Now, just because you see a cumulonimbus cloud, and we're going to cover clouds, but just because you see a cumulonimbus cloud doesn't mean, oh my God, a thunderstorm's going to develop. Now, if you saw those cumulonimbus clouds and you got the temperature inversion, high relative humidity, which we'll all cover that later in the series, then I would be sitting there like, there's a possibility some thunderstorms could occur. So then you start looking at your forecast and things of that nature. Okay. So we talked about the warmer air aloft. I got ahead of myself there. So that brings us back to our recap. We talked about temperature being very critical, and throughout this part of the video series, I showed you why temperature is critical. We don't want ice on our wings. We don't want ice on our runways. If we do have snow and ice on our runways, we want them plowed before we land airplanes on them. If we have very hot or high temperatures, we're going to need more runway because it's going to take us, this is what we would call a takeoff roll. or a takeoff distance. On a normal day, this will be the takeoff distance. Okay, the flat or horizontal part. The angular part is the rotation and takeoff. On a very, very hot day, we're going to need more runway, and our angle of ascent is probably not going to be that good. We talked about how the earth or the ground radiates heat and cold better than water. It's very, very hard, or it takes a lot more cooling or heating in order to get water to change. Or swampy areas, we talked about the swampy areas where that moisture resists the temperature change. We talked about Earth receiving solar radiation from the sun. We talked about terrestrial, I got it now, radiation. My little tongue-tied situation. We talked about the incoming solar radiation producing more heat at the equatorial regions than they do the polar regions. And we talked about that because up here, the same solar radiation has more ground to cover. So the heat is distributed a lot more. You're getting less bang for your buck as far as heating goes. We talked about temperature variations with altitude. We talked about temperature inversions when the lapse rate, back to temperature variations with altitude. As we increase altitude, we should lose temperature up to the point of the tropical pause. So, and then we talked about temperature inversions just being conducive for, among other things, we need other factors besides the temperature inversion. But when we're in areas of temperature inversion, high relative humidity, it's a recipe for a thunderstorm. At this point, I was going to be like, okay, like, subscribe and stuff, but since I kind of cut it off, we're going to jump into this part of atmospheric pressure and altimetry. Atmospheric pressure. We talked about atmospheric pressure before. Down here, we have high atmospheric pressure. At higher altitudes, we have lower atmospheric pressure. But what we have to do is we have to think of the atmosphere exerting force. Remember that pool example, and I think it was video 1 of this series. Down here at the pool, we got the whole weight of the surface of the top of the pool and all that water exerting pressure on us. When we swim maybe 1 feet above the surface, then we don't have as much pressure per unit area being exerted on us. Now, air is not a solid. If we think about, we have gases, which is air, solids, which would be the earth, liquid, which would be water. We can't really weigh air, can we? Well, at this point, we can't put it on the scale and weigh air. Like you would put your feet on the scale and be like, okay, I'm 180 or 220. We can't weigh air like that. So, a guy named Evangelista Torricelli came up with an apparatus that helps measure the weight or the pressure that the atmosphere exists. The pressure that exists at a certain level, I guess is what I'm trying to say. Basically, this is a container and there's mercury in it. And this is a glass tube that is evacuated. All the air is taken out. And what happens is the atmospheric pressure pushes down or exerts itself downward on the pool of mercury. And then what happens is the mercury is pushed up. So at sea level, we should have 29.92 inches of mercury, which is Hg is the symbol on the periodic table. So the element in here is mercury, and the air pressure exerts itself just by air just being in the environment. It's exerting pressure downward on the mercury, and then the mercury is being pushed up into the tube. Now this is more than 20. This is more than, I don't think he's that tall, But we just want you to know that if you had, say, like a 40-inch evacuated class tube and you had your mercury there, the atmosphere would push it up 29.92 inches or 76 centimeters. Whatever you measure by, either standard or metric. So this guy is Evangelista Torricelli. He created this apparatus. This apparatus is called a mercurial barometer. Like Mercury, the planet Mercury. Mercurial barometer. Okay. And that's what this thing does. It measures the atmospheric pressure, since we can't put air on a scale. Now, weather services, we have the National Weather Service, we have the National Oceanic and Atmospheric Administration. They make all our charts and maps in aviation. The Federal Aviation Administration and the Civil Aviation Authority. These weather services use two types of barometers that this guy came up with. The mercurial would be one, this one, and we talked about how that worked. And go on and on and on. Then we have an aneroid barometer. What we have here is a flexible metal cell. It's kind of like a foil type material, but this is the type of barometer that we have in aircraft. Okay, I don't think, with all the flight conditions that we could experience, we wouldn't want this thing measuring atmospheric pressure. And this is how altimeters work. I should have put a picture of an altimeter there, but this is essentially one. It's just not calibrated, and you can't see the altitude numbers and things of that nature. But this is basically, the altimeter is basically a aneroid barometer. All right, pressure exerts itself, and this is like partially evacuated, which means we put a little bit of vacuum pressure in there, so it can flex against the different atmospheric pressure changes. I'm just going to jump ahead, as we climb and descend, the higher pressure as we descend, or when we climb, the lower pressure is going to exert itself. So just the air being around this flexible metal cell that's being tied into a mechanism. There's a lever there and a spindle, and then it rotates the pointer. And you can freeze that and look on your own, but that is just driven by climbing and experiencing lower pressure, or a lower amount of atoms exerting themselves, and then descending, and then a higher amount, and then the needle goes down and says, hey, you're descending. So pressure variations, we need to talk about. Pressure varies with altitude. We talked about that. And we covered this. And there is a little bit of redundancy here, because I'm trying to hammer into this. I'm trying to make this as simple as possible. And if you guys are like, I still don't understand it, then I need to come up with a better way. So everybody, I want an 8-year-old to understand, well, maybe not an 8-year-old, but a 12-year-old at least. But as we move upward through the atmosphere, the weight of the air becomes less and less. If we carry a barometer with us, we can measure a decrease in pressure, as I just talked about. So you can read this on your own. You can read this on your own. Now, temperature also affects pressure, because we could have a standard temperature where the atomic particles are just kind of hanging out. If we get cold, or the temperature drops, then what's going to happen? The atoms are going to close in together. They're going to get closer together, and if it gets hotter, or warmer, I should say, then they're going to spread apart. So more volume is covered. All right. So that's one way of just looking at this. And typically when you think about it, we get warmer temperatures here, and in the standard atmosphere, as we increase, the temperature is going to drop and give us lower pressure. So hopefully we could see how that all ties in. You can read this on your own. It's in the book. And I'm just trying to think whether I should stop this now, because now we're going to go into a different area. So I will stop it now. Again, this is Kieno Thomas. Please like, subscribe, and share. And I thank you for watching Aviation Weather for Professional Pilots, or Meteorology for Professional Pilots. I'm not sure which one I'm going to name it, but we'll get to that. So at this point, thanks for watching.